Hello, this is a video on race condition. In this video, we will explain race condition in a couple of ways, and then we'll describe possible outcomes due to race condition, some of which can be disastrous. First, what is a race condition? A race condition is a phenomenon which occurs as a result of multiprogramming. A race condition occurs whenever two or more processes or threads read and act upon shared data, and the end result of that action may differ depending on the order in which the competing processes acted upon the data. There are two types. The first type we're going to talk about is check then act. This is when a shared value between two or more processes have been changed between the check step and the act step. A second type is read, modify, write. In the read, modify, write problem, this exists when two or more concurrent processes need to update the value of a variable based upon a previous value of the same variable. The first one we're going to demonstrate right now is the check then act.
Container represents a shared variable with the starting value of 6. The number of cookies is the value of the variable. Jason, Eric, and Amber are processes that share this variable.
We check the value of the variable at 6. I'm going to take one cookie, and that'll leave me 5 for later. The value of the variable is 5. I'm going to add my 3 cookies to the 5 cookies in the container. Now the variable has the value of 8.
Okay, let's check. I see the value of the variable is 8. I'm going to take 5 cookies. That leaves this value at 3.
Alright, I'm ready for my 5 cookies now. I need to go check for them. Craptastic! There's only 3 here. I have to abort. Ah!
The following screens illustrate the read, modify, write pattern for race conditions. We implemented the code in the following screens and demonstrated that a race condition may occur. This code creates a class with one variable and 2 methods: an integer shared variable, which is our shared variable, a method to get the value of the shared variable, and a method to set the value of the shared variable. This next class does 3 basic things. We create an instance of the shared variable. We create 1000 threads, all of which will increment the shared variable by 1. When the 1000 threads are done, we test the value of the shared variable. We expect the value to be 1000. Recall that Java will initialize the value of the integer to 1. We create a test harness that will repeat the test up to 10,000 times. The harness will stop executing the test when it detects a race condition occurred. Here we execute the test program. We see that on run 1, the 1000 threads completed their work and there was no race condition. Same for run 2, 3, 4, and so on. We actually had to execute the program 68,939 times in order for the race condition to occur. This next part is very important to understanding what happens in a race condition. At the end of the run, the value of the shared variable was 9,999, and it should have been 10,000. This means that a single thread read in the value of the shared variable, and that value was incorrect. It read in the value of the variable before another thread's changes were properly applied. So one of the operations was lost. This demonstrates how a race condition may occur. Since no race condition occurred in the original 10,000 executions, we had to change the number of tries to 100,000, and we had to change the number of threads to 10,000.
So a race condition might cause a weird count or result where you might lose your cookies, but can it really have a negative impact that affects people in the real world and not just the programmer adding some variables? It sure can, and it left millions in the dark when the power went out for a large area of the northeastern United States and Ontario, Canada in August of 2003. There was a power surge around 4:10 p.m. and within 30 minutes, power outages were reported that included Ontario, Canada, down to Michigan, and all the way to New York City. People were stranded in subways, elevators, streets and highways, and didn't have any running water. The first thought was terror because of recent events at that time, but that was quickly disproven. So what happened? Well, it'd be easy to blame another large company for neglecting their tree maintenance program because an overloaded power line sagged and made contact with the tree that wasn't properly trimmed. But earlier in the day, an operator corrected a telemetry problem in a monitoring tool and forgot to restart it. Now when alarms should be going off to alert operators, nothing was happening. The operators rely on the system and alarms, but the data doesn't show a problem and no alarms are going off. One failure happens after another, and they're becoming more frequent because of the increasing size of the power surges. The root cause was determined to be a race condition when two programs were able to get write access to the same data structure simultaneously. Once this happened, the alarm process was put into an indefinite loop so no alarms were going off and the operators were looking at old data. The process queue started backing up and this caused slowness on the system. So why do we care? This is old news and was patched. We're computer scientists and this was already fixed, right? Well, I'll let Bob answer this question.
How's it going, Einstein? That good, huh?
I don't understand what the hell is so important about history. It's all stuff that has already happened.
Without understanding of history, Alice will not know where he came from. Without understanding of history, Alice will not profit from mistakes of the past.